Hi everyone, let's talk about standard forms for equations of ellipses. Remember that the standard form for the equation of a circle centered at the origin is given by x squared plus y squared equals r squared if r was the radius, r is positive. Now, if we divide both sides by r squared, we could, in principle, write this as x squared over r squared plus y squared over r squared equals 1. But remember that for an ellipse does not have a radius, r, so we're going to have two different numbers here. And that's where we get this. This is the standard form for the equation of an ellipse centered at the origin that is horizontal, or x long. X squared over a squared plus y squared over b squared equals 1. Remember, for an ellipse, a is not equal to b. There's no common radius. Now, it's a horizontal ellipse if the larger denominator, the a squared, is under the x squared as opposed to the y squared. So, for example, if we have on the top here, x squared over 9 plus y squared over 4 equals 1. This is the equation of an ellipse centered at the origin, and it's going to be x long. Now, it should be straightforward to find the vertices if you set y equal to 0. All right, the x-intercepts, the vertices will be intercepts here. If you set y equal to 0, you get x equals plus or minus 3. If you set x equals to 0 and get the y-intercepts, you get y equals plus or minus 2. So look at that. Again, you have x-intercepts, the vertices, at 3, 0 and negative 3, 0. And you have intercepts at 0, 2 and 0, negative 2. Now, these are not vertices. These are endpoints of the minor axis, but they're good points to know. So remember, in this form of the equation, all right, we have a squared and b squared in the denominators. A squared equals 9, so a is 3. That's why the x-intercepts here are at 3, 0 and negative 3, 0. B squared is 4, so b is 2. That's why we have the y-intercepts here at 0, 2 and 0, negative 2. And again, because the larger denominator is under the x squared as opposed to the y squared, it's a horizontal or x-long ellipse. Now, if the larger denominator is under the y squared, then we would write it as x squared over b squared plus y squared over a squared equals 1. Again, you would have positive numbers beneath the x squared and the y squared, but this time the larger denominator, the bigger number, is underneath the y squared. In that case, we have a y-long or vertical ellipse, like so. So we have a units from the center to these vertices up here and down here, and b units to these endpoints of the minor axis over to the right and to the left. So for example, look at this. X squared over 4 plus y squared over 9 equals 1. The larger denominator, the 9, is under the y squared, so it's going to be y long. Okay, and look at this. The vertices are going to be on the y-axis here. That's the major axis over here. All right. We get vertices at 0, 3, 0, negative 3. Okay, a is 3. So we have vertices at 0, 3, 0, negative 3. B squared is 4 now. B is 2. And remember, a and b are positive by definition. If b squared is 4, then b is 2. 2 units over here, and then 2 units over here. So, and this is a y-long or vertical ellipse. The larger denominator, the 9, is under the y squared, not the x squared. Okay. So these are two different ellipses. Right? If you switch the denominators, then yeah, you can go from the red ellipse to the blue ellipse, and vice versa. Now, you can also change the center of the ellipse. In forms 1 and 2, the center was the origin. But just like in chapter 1, we can use the principles of translation to write more general formulas. If the center is at h, k in general, right, then we substitute or replace x with the quantity x minus h in both formulas, and we substitute or replace y with the quantity y minus k in both formulas. So for example, let's say we want to move the center from the point 0, 0 to the point 1, 2. We move the center from 0, 0 to 1, 2. H is 1, k is 2. H is 1, k is 2. So if we take this ellipse centered at the origin, all right, and if we go over here to the third equation, where we substitute x with x minus 1 and y with y minus 2, same denominators, don't forget the squares, or the equals 1, we go from the red ellipse to the green ellipse, where the center is now at the point 1, 2. Now what about the ellipse in blue? That centers at the origin, 0, 0. What if we want to move this ellipse, translate it so the new center is 1, 2? Well, once again, going from the blue marked ellipse here, we substitute x with x minus 1, substitute y with y minus 2, and we move the center from the origin to 1, 2. Remember, there are sign flips. Because we have x minus h and y minus k, we have sign flips. If we substitute x with x minus 1 and y with y minus 2, we move the center from 0, 0 to positive 1, positive 2. Whoops. No, that's correct. All right, so we go from the blue ellipse to the purple ellipse. The center moves from 0, 0 to 1, 2. So these are the more general standard forms for the equation of an ellipse centered at a more general point h, k. Remember, a squared corresponds to the bigger denominator, and it indicates whether we have an x-long or horizontal ellipse or a y-long or vertical ellipse. Don't forget the equals 1 on the right. The eccentricity of an ellipse describes how elongated the ellipse is, and it's defined as c over a. So for example, and again, we can think of a circle as being like a degenerate ellipse just for the sake of argument, all right? For a circle, c is 0. It's like the foci collapse onto the center. C is 0, and therefore the eccentricity is 0. In fact, for a circle, the eccentricity E is 0, even though we don't call a circle an ellipse. Here, we have a slightly elongated ellipse. E is 0.3. So the center is fairly close. Sorry, the foci here are fairly close to the center. They're much closer to the center than the vertices are over here. Basically, the foci are 30% away from the center compared to the vertices and their distances from the center. The distance here is 30% of the distance here. E is 0.3, so we have slight elongation. If E is 0.8, we have substantial elongation. Okay, C is 80% of A. C is 80% of A. The distance from the center to each focus is 80% of the distance from the center to each vertex, which indicates strong elongation. Now we have comets that have very eccentric orbits where E might be 0.999 something. The sun, by the way, would be at one of the foci. That's one of Kepler's laws. All right. So E for an ellipse can be a real number strictly between 0 and 1. Remember that C, the distance between the foci and the center, must be less than A, the distance between the vertices and the center. The foci are closer to the center than the vertices are from the center. So we know C is less than A, and they both have to be positive by definition. If we divide all three parts by A, 0 divided by A is 0. C divided by A is E. That's how we define E, the eccentricity formula. By the way, E here is not 2.718. It couldn't be for an ellipse. E here is for eccentricity. A divided by A is 1. So E, the eccentricity of an ellipse, is a real number strictly between 0 and 1. The closer it is to 0, the more circular the ellipse is. The closer it is to 1, the more elongated the ellipse is. So These are the various pieces for analyzing an ellipse in the xy plane. Next, we're going to work with an equation of an ellipse directly.